To find f inverse x, we will need two things. One is the expression for f inverse x. The other one is going to be the domain of f inverse x. And the domain of f inverse x is the same as the range of f. So let's find the range of f first. I'm going to draw the graph to find its range. So if I were to sketch out the graph, this is going to be the x-axis. My y-axis is going to be, let's say, here. For this, there's going to be a horizontal asymptote of 3 over 3. So the horizontal asymptote is 1. So let me draw in the horizontal asymptote. And this is y is equal to 1. It has a vertical asymptote, and the vertical asymptote based on the denominator here, it is also 1 because 1 will cause the denominator to be equal to 0. So we have a vertical asymptote, x is equal to 1. So here, x is equal to 1. And if I were to sketch it on my graphing calculator, the shape is going to look something that is like this. It will cut the y-axis very close to the origin and coming down here. So I'm going to not draw this side of the graph because according to what the question says, for fx, x is supposed to be strictly less than 1. So this graph here is my graph of y is equal to fx. And reading the y coordinate that I can see from here, we can know what is the range of fx. The range of f, the range of the function f, is going to be from minus infinity all the way until 1. So from negative infinity to 1, not inclusive of 1. So this settles for us the domain of f inverse. Let's next try to find the expression for f inverse. And to do that, I'm going to be letting y be equal to fx, which means that y is going to be equal to 3x minus 1 divided by 3x minus 3, such that x is supposed to be less than 1. So let's try to make x the subject. Cross multiplying, we have a 3xy minus 3y. This is equal to 3x minus 1. Bring this over to the left hand side and bring this over to the right hand side. We will have a 3xy minus 3x. This is equal to 3y minus 1. So factorizing out x, then it will be 3y minus 3 is equal to 3y minus 1. So making x the subject is going to be this divided by 3y minus 3. So this will give us the expression for f inverse. So f inverse x will have an expression. I'm going to replace all the y here by x. It is going to be 3x minus 1 divided by 3x minus 1, such that x belong to all real numbers for x to be strictly less than 1. So I have my f inverse here. And now we are supposed to prove that f2x is equal to x. But let's not misunderstand that f2, this 2 here is square, it is not. f2x represents a composite function, f x. And if you were to look at part 1, what we can see is that for f inverse, it actually has the same expression as fx. And its domain is also going to be exactly the same as fx, which means that fx and f inverse x, they are actually equal functions because they share the same expression and the same domain. So I can actually rewrite this, let's say this f that is here, I'm going to rewrite this as f inverse based on the result that we have obtained from part 1. And what is f inverse? This is equal to x. So we have shown what the question wants us to show. And by making use of this, I'm going to try to evaluate f2017. So this once again is a composite function. It is going to be compositing itself for 2017 times. If I were to break up this composite function into 2015 times of f20, then we can make use of this result here, because f2x is going to be equal to x, which means that f20 is going to be equal to 0. Okay, this entire thing is going to be equal to 0. So here we have a 0, and we can continue, right? Because I can also rewrite this as f2013 of f20, and f20 is 0. So I'll be getting a F2013 of 0. So in fact, from 2017, we will minus 2, we will minus 2 again. So we will just need to keep minusing 2 and I will land up with just a F since this is an odd number. So if I were to just keep minusing 2, minusing 2, minusing 2, we'll be doing a minus 2016 times. That leaves me with an F of 0. And F0, now we can make use of this. It is going to be 3 times of 0 minus 1 divided by 3 of 0 minus 3. So we'll have a negative 1 over negative 3. My answer is going to be equal to 1 over 3. In part 3, we are analyzing this as a composite function. And to analyze its existence, I'm going to make use of what we have discussed on the Achevas TV theory outline. So for the composite function fg in general, if it were to exist, then on the Achevas TV outline, I drew a schematic that was like this, where x will first go into g, then after that it goes into f. So this is where the two functions are going to be connected. And what I want to make sure is that everything that comes out from g is going to be possible to go into f. So it depends on the domain of f. So I want to make sure that this happens in order for the composite function fg to exist. We already have the domain of f. It is given to me as x to be less than or equal to 1. What we don't have is the range of g. So what we want to do is to find the range of g. And to find the range of g, I'm going to sketch a graph for g. So if I were to sketch that graph for gx, it is going to look something that is like this. This is the x-axis. This is going to be the y-axis. And my graph is going to look like this. Okay, here is going to be a solid dot. And this is 2, 0. When x is equal to 2, the output is going to be equal to 0. And when x is strictly less than 3, so here I have a hollow dot. This is 3 and 1. So this is the graph of y is equal to gx. And by reading all the possible y coordinates, we can see what is the range of g. The range of g is going to be from here all the way until here. So it's going to start from 0, and it can be equal to 0 and all the way until 1, but not inclusive of 1. So now comparing this to this, we can see that they are a subset. So range of g, which is from 0 inclusive all the way until 1. And the domain of f is anything that is from negative infinity to 1, not inclusive of 1. This is going to be a subset. Therefore, we can say that the composite function fg, this composite function here, it exists. And we are supposed to find the expression for fg. And this is easy. We just need to put the expression for g into the x of f. So for fg, for fgx, the expression will look like this. It is going to be 3. X is going to be replaced by this. So square root of x minus 2, then minus 1, divided by 3 of square root of x minus 2 minus 3. This is the expression for fg. How about the domain for fg? If I were to look at this again, the domain for fg is what that goes into here. And this is defined by the domain of g. So the domain of fg is going to be the same as the domain of g. So let me quote it here. Domain of fg is going to be the same as the domain of g. So it is going to be from 2 all the way until 3. And we want to find the range of fg. And since we have the expression for fg and the domain for fg, let's just sketch fg as one function. And we'll make use of the graph to find the range of fg. Let me sketch the graph here. If I will sketch this graph on my graphing calculator, I will get something that is like this. Let me show you guys. So I have this, and my y-axis is going to be here. My y-axis, this is my x-axis. My graph is going to be something that is like this. But if you were to take a look at this, when x is equal to 3, then this is going to be square root of 3 minus 1, which is 1. And 3 minus 3 is going to be equal to 0, which means that we actually have a vertical asymptote. And the vertical asymptote is at x is equal to 3. And my graph is going to look something like this. Okay, then you will tend towards the vertical asymptote when x is equal to 3. It is bigger or equal to 2. So here is going to be a solid dot 2 and 1 over 3. This is y is equal to y is equal to fgx. So the composite function fgx. So reading from this graph, we can then deduce the range of fg. And the range of fg is going to be from minus infinity all the way until the y coordinate of this is 1 over 3. And since it's a solid dot, we know it is inclusive of this 1 over 3.